Welcome to The Explainer. Today, we are diving headfirst into one of the biggest, most mind-bending mysteries in all of physics. It's this nagging problem. The fact that our universe seems to be expanding at two different speeds at the exact same time.
So let's just kick things off with a pretty wild idea. What if our universe, the one we see and live in, isn't the only one? What if we're actually caught in some kind of strange, empty pocket of space, stuck between two totally different cosmos, each playing by its own set of rules? Now that might sound like something straight out of science fiction, but it's a real possibility some scientists are seriously considering. And it's all because of a problem they call the Hubble tension. You see, when they try to measure how fast our universe is expanding, they keep getting two different answers. On one side, when we look at the oldest light in the cosmos, light from the very beginning of time, all our best models predict an expansion speed of about 67 kilometers per second for every megaparsec. And a megaparsec is just a massive cosmic yardstick, about 3.3 million light-years. But, and this is the big but, when we measure the galaxies right here in our local neighborhood, we get a faster speed. We get about 73. Okay, so here's the part that makes this a real crisis. Both of these numbers have been checked, double-checked, and triple-checked by different teams using different instruments. The measurements are solid, so this isn't some simple mistake in the math. No, this points to something fundamental about the universe that we just flat out do not understand. All right, so to really wrap our heads around this mystery, we've got to rewind the clock. We need to go back and see how we even figured out the universe was expanding in the first place. Our story really kicks off more than 100 years ago, and it's built on the work of some true giants. You've got the incredible genius of Albert Einstein, a brilliant physicist and soldier named Carl Schwarzschild, and of course, the legendary astronomer Edwin Hubble. I mean, just try to picture this for a second. It is 1916, in the thick of World War I, with bombs literally falling around him in the trenches. Carl Schwarzschild manages to do something that even Einstein himself hadn't figured out yet. He found the very first exact solution to the equations of general relativity. And hidden deep inside his solution was the first real mathematical proof for one of the most bizarre and extreme objects in the entire universe, the black hole. You know, a concept that is absolutely fundamental to how we see the cosmos today. So the next big clue came out of this huge scientific argument at the time, famously called the Great Debate. Astronomers kept seeing these little fuzzy patches in the night sky, right? Like the one in the Andromeda constellation. And they just couldn't agree on what they were. Were they clouds of gas inside our own Milky Way, or were they something much, much farther away? Well, that debate was finally put to rest by Edwin Hubble. He used a really special kind of star called a Cepheid variable. Now, these stars are amazing cosmic tools. They actually pulse, they get brighter and dimmer, and the speed of that pulse is directly tied to how bright the star truly is. They're basically standard light bulbs for the universe. So Hubble spotted one of these Cepheids in Andromeda and used it to calculate the distance. And the number he got back was just staggering, 2.2 million light-years. This proved it was way, way outside our own galaxy. And just like that, with one observation, Hubble showed us that the universe was filled with countless other galaxies and was unbelievably huge. But Hubble didn't stop there. He kept measuring the distances to more and more galaxies, and he noticed this incredible pattern. The farther away a galaxy was, the faster it seemed to be racing away from us. This became known as Hubble's law, and it was the first solid proof that our universe isn't just static, it's actually expanding. Okay, so building on that amazing groundwork, modern astronomers have taken Hubble's techniques and refined them to an insane level of precision. And this gives us one side of our cosmic disagreement, the measurement of our local universe. They use a method called the cosmic distance ladder. It starts with those super reliable Cepheid stars to get the distance to nearby galaxies. But then, inside those same galaxies, they look for something even brighter, Type Ia supernovae. These are exploding stars that are so ridiculously consistent, they can be used as even more powerful standard candles to measure distances clear across the observable universe. So, using this latter method, teams with the Hubble Space Telescope and now the James Webb Space Telescope have totally locked down the local expansion rate. They are incredibly confident in their answer, and it consistently lands right around 73. So, if the answer from looking right around us is a solid 73, where in the world does that other number, 67, come from? Well, to find that, we have to look in a totally different direction. We're not looking out into space anymore, we're looking back in time. What you're seeing here is, for all intents and purposes, a baby picture of the universe. It's the oldest light we can possibly see, a snapshot of the entire cosmos when it was just a tiny infant, only about 380,000 years old. This ancient light is called the cosmic microwave background, the CMB. You can think of it as the leftover glow from the Big Bang itself, and hidden in its tiny little temperature patterns is basically a complete blueprint of the early universe. All its initial ingredients and conditions are encoded right there. So what scientists do is they take this incredibly detailed baby picture and they plug all that data into our best theory of the universe. This is a framework called the lambda-CDM model, and it includes things like dark matter and dark energy. Then they basically hit fast forward, simulating 13.8 billion years of cosmic evolution. And here is the crucial difference. This method doesn't measure the expansion today. It uses the physics we know from the early universe to predict what the expansion rate should be. And every single time they run these calculations, the prediction comes out remarkably consistent, right around 67. And that, right there, is the heart of the cosmic crisis. A direct local measurement gives us 73. A rock-solid prediction based on the dawn of time gives us 67. If both of these are correct, and the evidence says they are, then it means our fundamental theory of the cosmos, our rulebook for how everything works, must have a chapter missing. And this isn't just some abstract debate over numbers either. It has huge implications. For instance, a faster expansion rate means a younger universe. But if the universe is only 12.6 billion years old, we have a massive problem, because we know for a fact there are stars out there that are over 13 billion years old. How can a star be older than the universe it's in? It's a paradox. It just doesn't make sense. So, this paradox strongly suggests our cosmic rulebook needs some edits. To figure it out, scientists are looking at a whole lineup of prime suspects. Could there have been some kind of early dark energy that gave the universe an extra kick right at the beginning? Or maybe new undiscovered particles that changed the cosmic recipe? Or what if we just live in a weird part of space, a cosmic void that's less dense, making things around us appear to expand faster? This isn't some niche problem that's going to fade away. It's actually one of the absolute hottest fields in science right now. In fact, brand new, powerful observatories like the Roman Space Telescope and Euclid are coming online specifically to gather more data and help us crack this cosmic case. When it all comes down to it, the Hubble tension isn't just about a number. It's forcing us to ask a question that is both deeply scientific and profoundly philosophical. Where are we really? And what is the true nature of this universe we call home? It seems the answer is still out there, just waiting for us to find it.